learning about integration. In our last lectures, we have learned about differentiation. Now we will be knowing about integration. Now, in order to understand integration, it is mandatory and as well as necessary to actually understand the concept of like differentiation at first. So if you don't know or if you have forgotten, then I would urge you to actually go back to the previous lectures and go through them to have a glimpse of what differentiation means and how like differentiation works. Now, integration is actually the opposite of differentiation. So in differentiation, what did we do? We actually found the rate of change, isn't it? The rate of change in differentiation, we actually find the rate of change. Okay, or which in our simple term we know it as gradient. Okay, gradient. Now, integration is the opposite to that. That means if we were finding dy by dx, now we like from the initial function fx, we are finding, let's say from our initial equation of y, we are trying to find dy by dx. If this is known as differentiation, if we're in differentiation, then the opposite of that is known as integration, or some sort of the same thing. This is not exactly the definition, not the exact definition, but 80% of the concept comes to this like cycle. I'll be coming back to that, like why the rest 20% has some issue. But so far, consider that if forward is like differentiating y to dy by dx, then integrating dy by dx gives us back to the returns us back the actual equation. Okay, that's known as our integration. Now, integration, let's say we have this function of dy by dx of something. Okay, dy by dx is something, something, let's say this equals to 1. dy by dx is equals to 1. Now, if we want to integrate this, integration sign is this, like this sort of a cursive f. Like in cursive, what do we have? F as this. So instead of that middle line, this is known as, like, this is the integration sign, where we usually tend to have limits. Okay, we will be coming back to limits after a bit later, but for now, let's stick with our basic concepts at first. Just give me a second. Yeah, so basically, since this is the integration sign, and if we want to find the integration of dy by dx, and our dy by dx was initially what? 1. Our dy by dx is given as 1. Okay, so then how do we find the integration and what should be the result? Now, in our simplest form, we have to integrate both the side. Like what? Like remember, if we have something that's y equals to 2 plus 3, if we multiply 2 with the left side, what do we need to do? We also need to multiply 2 on the right side, isn't it? We need to do the same on both the sides. Why? So that when we like divide both with 2, like the equation doesn't change. Okay, so have the equality in both the sides. We need to perform same operation on like either side of the equation. Similarly here in differentiation, in order to have the consistency and equality in both the sides, we have to perform integration on both the sides. Now, integration could be done with respect to only one base. Remember, remember this. The integration can only be done with respect to one base. Now, what do I mean by that? That means we can at a time integrate with respect to only one variable. So if we know the change of y, we can only if we have, let's say, in this case, if we since we have dy by dx, we can at a time integrate only one variable. That means either x we could be we could integrate, we can we can integrate or the change in y we can integrate. So either we have to take dx as a constant. So if dx is a constant, then we will say 1 by dx. Here dx is, let's say, some c is constant. So this is considered as integration of c dy. That means c can come out to the outer part. And now we are dealing with the dy part. Okay. Now, always remember, if nothing is given here, then there's an imaginary 1 here. Okay. Now, integrating this 1, what should we get? Integrating this 1, we should get some value which is a power, we should get a value of y to the power of something. Now, integration, when we are integrating some variable of some function, we are integrating the differentiated version of that function, or we are trying to get the area of the curve. Integration simply means the area under the curve. In differentiation, what did we do? We were finding the gradient, okay? The gradient of the curve. Now, integration means simply the area under the curve. That means this region area under the curve. Now, how do we find the area of the curve? So let's make this much more simpler. Let's say this is a straight line passing through the origin. If we extend this part to the x-axis, now what do we get? We get a simple triangle. Now, how do we find the area? We know the formula of finding an area of triangle is half into this base area, this base into this height, isn't it? So half times base into height. This is the area of the triangle. Now, if we have, let's say, some equation here, y equals to x, okay. Now, integrating this should give us also this area under the straight line, okay? Under the straight line, that should also be given. Now, if we are integrating this y equals to x, and remember, let's say we have, we want to integrate this equation, and we have to put integration sign on both the sides, okay? Let's make this a bit clearer. So we have a function, let's say y equals to x. Now, and the equation looks something like this, y equals to x, okay? Now, integration, the formula is something like this. We are integrating this this equation of y equals to x and y equals to x. We are integrating this. That means we do need that sign on the both sides. Now, with respect to what we should integrate, on the left side, we have the variable of what? Y. So we want to integrate this in terms of y. So we have to place a dy on the left side. Similarly, on the left side, we have x, and we need to differentiate this with respect to x, because remember, I just told that in integration, we can take only one variable, and with respect to that variable, we can simply integrate. Since we have x here, that means this is the closest call is to simply integrate this with respect to x. That's why we are placing a dx here. That means we are considering this x is the differentiated version, and we are going to the backward direction, integrating this x, okay? That's how it works. Now, for the formula, how it works, or the general formula of how integration works, the general formula of how integration works, we need to know certain formula. So let's erase this first, because directly doing maths won't make any logic. So we'll be doing and learning. So at first, I'll be showing the formulas, like which formula we will be dealing with, and how we are going to perform the operations. So the most common technique for finding these integrals, or this is known as the integral. Okay, so if we are, let's say, finding someone's integration, if this is our y equals to x and we are finding the integration, the result is known as the integral. Okay, so the integral of a function represents, actually, we just got to know that the integral of a function is the area under the curve of that function. So this is the function, and the equation is this. The integral of this function should be what? The area under this curve. So integral is equals to area under the curve. Okay, so far so good. Now, like the most common technique for finding these integrals is to using the power rule of integration. Now, what is the power rule of integration? So power rule of integration looks something like the following. So let's say we have a function y equals to, or an equation y equals to x to the power n, okay? Where n itself, we're defining the domain for n, that n cannot be equals to negative n, okay? So n is not negative n in this situation. For power rule, okay, only for power rule, n cannot be equals to -1. There are other rules where n could be -1, but for this, n cannot be equals to -1. Then the integration of this equation should be something like this. So we are simply considering the right side of the equation first. So right hand side. So integrating that x to the power n. Now, since we have the variable of what? X, and that n is simply the power. N is not a variable. N is some numerical number. So n could be 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 0, anything. Okay, but n is not like a variable. N is simply a numerical number, any numerical number, but x is a variable where x currently we don't know. Okay, like n represents any sort of numbers. So we can simply do the calculation using x to the power 2, also x to the power 3. Now, considering all of these values, we're just simplifying, generalizing that. That's why we're writing x to the power n. Now, then with respect to whom should we be integrating x? We should be integrating it with respect to x exactly. X should be integrated with respect to itself, because x is the variable itself. So the closest call and the closest way to integrate it simply is to integrate it with respect to x. So we are placing the dx here. It is a convention that if we are trying to integrate something, we have to place the variable, like the rate variable or the differentiated term of that variable, to the last of that expression, to the ending of that expression. Okay, so we have to simply multiply it sort of in that way. Okay, we're just multiplying it. Now, multiplying it should give us, now follow this part very attentively. Here, we should increase the power by 1. Okay, before going to that, let's recall the differentiation at first, because that will be much more easier for us. What did we do over here? If we have a function y equals to x to the power, let's say n, if we differentiate it, what do we get? Using the power rule formula, or the power rule. Simply what happens? The power comes in the front, isn't it? And we multiply with that term x to the power n, the power gets reduced by 1, isn't it? N times x to the power n minus 1. Isn't this the differentiated formula? Now let's say we have y equals to x to the power n plus 1. How do we then differentiate this? Using same formula, the power comes in the front, n plus 1, and the power gets reduced by 1. So n plus 1 minus 1, isn't it? This minus 1 minus plus 1 gets cancelled out. Simply we have what? N plus 1 x to the power n, isn't it? That's how it works. Now, if we are trying to integrate, let's say this one, this expression. Okay, if we are trying to integrate this expression simply, what should we get? Obviously, we should get this equation, isn't it? So, integrating, let's say this is our dy by dx part, like our dy by dx is what? N plus 1 x to the power n, isn't it? Now, we have to integrate both sides, isn't it? But at a time, we can integrate only one variable. Now, see how many variables do we have here? Here we have a y variable and x variable. Now, on the, like, try to observe on the right-hand side, the only variable we have what? X, isn't it? So we can simply take this variable of x or the dx part to the right side so that all the x's are together and all the y are together on the other side. So simply doing that, dy, like doing cross multiplication. So we have dy equals to n plus 1 x to the power n dx, isn't it? Now we can do the integration. So we are integrating in both the sides. See, now everything is like simply forming in that power rule formula. What's the formula? Like, see, here we have dx multiplied with the integrated part, like the integrating part. This is the integrating part. Like we are going to integrate this with respect to what? The dx. Okay. And on the left side, we are going to integrate this part with respect to y dy. And remember, we have an imaginary 1 here. Okay, imaginary 1 is there. Now, integrating this should give us then what? Like we have, like we simply got this expression from where? Differentiating this part. So integrating this should give us what? The left side should give us the y, isn't it? That should have happened. Integrating dy, that means we should get the previous value, and previous value is what? Y. So y equals to, and integrating the right hand side. Right hand side is what? Forget about this like dx part. Okay, forget about this dx part. Just consider this portion because this is that part. So integrating this should give us what? X to the power n plus 1, isn't it? So x to the power n plus 1, isn't it? That should be our integrating part. So if we write this much more clearly, so differentiating y equals to x to the power n plus 1, differentiating this give us n plus 1 to the power into x to the power n. Okay, that means now if we integrate this dy by dx, also remember here we do have a imaginary 1, isn't it? Now, why do I say that? The reason I say that because like there is another way we can like define this. Okay, there is another way we can also define this equation. On both sides, let's say we have our like differentiated that d value. Now d means what? Delta. Delta means what? Change. As I mentioned earlier, that if a curve, in a curve, we can take 2 points and find the difference. This is known as the del y. This horizontal part is known as what? Del y. Delta sign is represented as this, the del y. And this horizontal part is represented as delta x. That means change in y by change in x. The delta sign is also represented as this smaller triangle. So smaller triangle, that is delta y. So del triangle y, that means delta y, that is change in y, divided by delta x. Now, if we let's say reduce this difference to this point, again to this point, like if we minimize the difference between them, and it becomes so much like it becomes so much possible that the difference in them is so negligible that the change in y is almost equivalent to 0. The change in x is almost equivalent to 0. So del y is almost equal to 0, almost equal to, okay, I'm not saying exactly equal to 0, but almost equal to 0. And del x is also almost equal to 0. That moment, this del y by del x becomes dy by dx. Okay, that's the main like term. So that means we can simply say differentiating both the sides. So here we are differentiating this part, and on the right side we're simply differentiating what? We're like differentiating both the sides with respect to x. So this should give us x to the power n plus 1 divided by dx. Okay, because that's actually the main formula how it came. Now on the right hand side, we do have that x terms, isn't it? So that means we don't need to introduce any more like variable here. So we can simply differentiate that part, n plus 1 comes in the front, and we're differentiating with respect to x. That means what? We would get x to the power n. But on the left side, what do we have? We don't have any x terms. We just have a y term, isn't it? So differentiating in with respect to x, that means we need to have this portion dy by dx multiplied with a 1. Why 1? Because we are differentiating also y. So differentiating y, just simply consider differentiating y exactly as this formula x to the power n. What do we get? X to the power n, when we differentiate this, we get n comes in front, multiply with x to the power what? N minus 1. The power gets subtracted. Similarly, if we, let's say, differentiating y, what should we get? Consider y has a power of 1. 1 comes in front, and the power gets reduced to 1 minus 1. Becomes what? 1 into y to the power 0 equals to 1 times 1, which is 1. That's how it works. Okay, so what we saw in the previous lectures was a simplified version, but the actual method is this one, that we're differentiating the both the sides, because that's how it works. We need to differentiate, like if we perform an operation on one side, we have to perform the same operation on the other side, isn't it? So we are doing the same thing. So that means since we don't have a x variable on the left side, we have to introduce a dy by dx here. Like consider dy by dx a separate variable. Multiply this with the differentiated value of y. Now differentiated value of y is what? 1. So that's how it works. Okay. Now let's change the plot a bit. If we were to differentiate with respect to y, then how should have things like occurred? Consider again this equation. Let's say y equals to x to the power n plus 1. Now let's switch the sides and write x to the power n plus 1 on the left side equals to y. Now let's say instead of differentiating with respect to x, we are differentiating with respect to y. What should have happened? So we should consider what? X at the top, y at the bottom, isn't it? So the same thing happens like on the both sides. We would differentiate this part with respect to y and this part with respect to y. Okay. Now, if that's the case, then we do have a y on the right side, and we're differentiating that with respect to y. That means we don't need any other separate variables. We can simply just differentiate this y with respect to itself, so it gives us this result. And consider on the left side, we don't have any more y, isn't it? Since we don't have any more y, that means we have to introduce this variable dx by dy. Why dx on the top? Because we are differentiating x with respect to y. Okay, we are differentiating x with respect to y. That's why dx on the top, dy at the bottom. We are multiplying this with the differentiated value of x to the power n plus 1. So x to the power n plus 1, what is the differentiated value of x plus 1? X to the power n plus 1. We have seen just in the previous slide that this gives us the value of n plus 1 comes in the front, and x to the power n plus 1 minus 1. So 1 gets cancelled out, and n plus 1 into x to the power n, isn't it? So that's our result to the power n. So finally, we get to write dx by dy into n plus 1 times x to the power n equals to 1. So we can simply say that dx by dy is equals to what? 1 divided by n plus 1 x to the power n. So this is our dx by dy value, okay? Our differentiated value of x with respect to y, this is our result, okay? Now, if we want to find then the opposite, differentiated value of y with respect to x, that's the exactly opposite to that, which you can just simply flip this actually to get the result of dy by dx is actually flipping the result. So that gives us n plus 1 x to the power n. Okay. If you didn't understand, then rewind, pause the video and rewind and go through the video, like the part again. You will definitely understand, because this is a very crucial point. Like this is a very important concept. So in order to understand integration part, we have to at first understand this part. So I guess now it's clear why, like how this y equals to d, like I say, x to the power n plus 1, this dy by dx comes, isn't it? So we're actually differentiating all the sides with respect to x. Okay. Now, since there is the x on the right side, so differentiating x with respect to x, we don't need to like do any more conversion. So we can simply just write n plus like the differentiated value of this x. But on the left side, like it is something like money, let's say like money conversion. So we have taka and dollar. So in order to like have the equivalency taka and dollar, we have to convert one currency to another, isn't it? Because all the currencies are not the same thing. Bangladeshi taka is not equivalent to like US dollar, isn't it? So we have to do some conversion. So let's consider y as taka and x as dollar, or vice versa. So similarly, since we don't have a x variable on the left side, so we will have to multiply our dy by dx here, and differentiating y gives us what? 1. Like writing 1 and not writing 1, like multiplying 1 and not multiplying 1 is the same thing, isn't it? We can just simply write dy by dx equals to n plus 1 x to the power n. Okay, so that means what? These are actually a variable. Now, if we want to integrate them, then how do we deal with them? Simply, we have to integrate with both the sides, like the way we differentiated both the sides. So we have the 1 here, and dy by dx equals to what? Integration of n plus 1 x to the power n. Now see one thing, this 1 is what? The differentiated value of y. But this n plus 1, this is a constant, isn't it? Obviously, this 1 is a constant, but we do need that 1. But consider here, x is the variable. The power stays with x, but this n plus 1 is in a multiplied format, isn't it? This is multiplied with the x. So we can simply do what? Bring that n plus 1 in front of this integration sign. That means, like, this does not have any effect, because remember, if we have a constant, let's say 5, if we differentiate this 5, what do we get? We get a 0, isn't it? Why? Because we have imaginary x to the power 0 here, and when we differentiate this, that 5 stays 5, that 0 comes in front, and x to the power 0 minus 1. Now 0 multiplied with anything becomes what? 0. So that's why we got a result of 0 there. So similarly, this concentration does not have any have any effect on integration or differentiation. So that will come in front. What we consider is that x to the power n. Okay. Now, as I've mentioned earlier, that we have to differentiate, we have to integrate with respect to either of the variable. Okay. Similar to the differentiation part. In differentiation, what we did, what did we do? We differentiated with respect to just a single variable. Like consider this part, we differentiated on the right side with respect to x. Similarly, we differentiated on the left side with respect to x. Since we didn't have any x on the left side, we introduced this dy by dx so that we can differentiate that y. Okay. Same goes for like to the right side, like to the integration part. Since we don't have, like we can only integrate with respect to one variable, we will move all the x's to one side and all the y's to other side. So all the x's, we have a dx here, so we are moving that dx to the right side as well. So we get n plus 1, and we need to, sorry, that should be dy equals to n plus 1, and there goes x to the power n. And we have to remember, like we have to insert that dx inside that like integration part. So if you consider this as a bracket, we have to consider like this is the bracket of, let's say, the integration part. Like the integration is applicable only inside this bracket, and over here also this integration is also applicable inside this bracket, and that's why we need to like insert that dx inside that integrated or the integration function there. Now we can simply just integrate. Now, integration of them should give us what? This, isn't it? Now see how the magic happens. Integration of y with respect to dy. Remember, we got 1 with respect to what? With respect to, like, differentiating with respect to y, isn't it? Like, we got that dy by dx because we were differentiating everything with respect, like all the sides with respect to x. But since we didn't have x on the left side, but we have a y, we need to integrate, we need to differentiate that y. So we also differentiated that y with respect to itself. So how that actually happened? Like, the thing actually happened in this way. How do I explain this? Yeah. So what happened actually was, like, over here, if I, like, elaborately or describe this much more clearly, we introduced the variable dy by dx, but since we don't have any variable here, what do we have here? We have a dy there, isn't it? So we will differentiate that y with respect to whom? We need to, like, differentiate a variable with respect to itself so that it completely vanishes. So that means there is a y, we need to differentiate that y with respect to itself. So we will differentiate that variable with respect to itself. Okay, we are differentiating that variable with respect to itself. So this is the main part which we, like, because of which we got that y, like y, differentiating y with respect to itself becomes what? 1. So that's why we get a 1 here. Okay, that's the main, like, concept. So that means if we differentiate y with respect to itself, we get a 1. Now if we then integrate 1 with respect to dy, we should get what? Y, isn't it? Like, isn't it the exactly inverse, like the reverse, the inverse thing, like opposite of each other? We differentiate y with respect to itself, and we get what? 1. That means if we integrate this 1 with respect to y, we should get what? Y, isn't it? Integrating something with respect to y should give us a value, a variable of y, a term of y, and differentiating a variable or a value or expression of y should give us something with respect to y. So integrating this 1 with respect to dy or with respect to y should give us what? Just do the opposite. What happens? Like, how did we get 1 in the first place? Like, 1 means what? We have an imaginary y to the power 0 here, isn't it? So here we have a y, like 1 times y to the power imaginary 0. Why? Because anything to the power 0 is equal to 1. So that's how it works. Now, differentiation was what? We subtracted the power. So that means we have to do what? We have to add a power, add a 1 to the power here. So that means we will be adding, like in integration, we will be doing the opposite. In differentiation, we did what? If y is that, then differentiating that gives us what? That y to the, like 1 comes in front times y to the power 1 minus 1 gives us what? Y to the power 0. Now, in order to get that y back, y to the power 1 back, what do we need to do to the y to the power 0? We have to add 1, isn't it? And what do we have here? 1 in the front. That means what? We have to divide that 1 by 1 so that that gets eliminated. Like, think it in this way. Let's say we have y square here. Okay, y square. So differentiating this, like this y square should give us what? That 2 should come in front, and y power should, the power of y should get reduced by 1. So 2 minus 1, that means what? 2 to the power y, isn't it? Now if we want to go back to that portion, see what's the difference. Y has a power of 2 in the initial function, and the 2 vanishes. That means what? We have to increment the power of y with 1 so that we get 2. And in order to, like, eliminate this 2, we have to do what? We have to divide, like, that 2 by 2, isn't it? Because if we divide 2 with 2, that gets cancelled, isn't it? So that's why integration is simply doing the reverse, like, operation. Okay, it's sort of reverse engineering so that we get the initial function back. So that's what is happening here. So integrating this gives us simply y to the power 0 plus 1 divided by 0 plus 1. Simply multiply, like divide that power. Okay, that's a like much more convenient way of like saying whatever you add to the power, simply divide the whole expression with that power, the new power. Okay, that will like do the work for you. Similarly, on the right hand side, we have what? N plus 1. That's the constant. But here what do we have? We have to increment the power by 1. So x to the power n plus 1. And what did I say? We have to divide the whole thing with what? The new power. So the new power is what? N plus 1. N plus 1, isn't it? Now see, this n plus 1 and this n plus 1 are the same. So they can get cancelled out. Okay? So if they get cancelled out, this y to the power 0 plus 1 is what? That's actually y to the power 1. So that means that's y. And 0 plus 1 means what? 1. And anything divided by 1 is what? That remains same. So y divided by 1 and writing just y is the same thing. So y equals to what? X to the power n plus 1. See, we just got our initial function back. So these are the same thing. The differentiation and integration are exactly opposite to each other. But like there is a but there. So this is not exactly what it should be, but for the time being, that's how the like power rule implements. In the next video, we will learn what is the extra part of the integration.